Hi guys, welcome to the next installment of the curse of the DAS18 amplifier. This thing, yeah. It's like an ongoing soap opera, this one, yeah. So, power supply repaired works. All powers up, connected to the amplifier, it all powers up. But I don't get any audio out, nothing goes bang. But nothing goes anything, the speakers are silent, yeah. I can see that on here, this goes to the mixer board. Whether it's connected to the mixer board or whether it isn't, I have 0 volts on the audio in, the red one I think it is. And I have about 8 point something volts on the other one. And that's not right, I think. All the supply voltages are present. We have the plus and minus 15, we have the plus and minus 55 or 6 or something like that, the high voltage. All the voltages are there then. These chips are effectively a Class D amplifier in one chip. So you have audio coming in and then you have drive coming out to the MOSFETs, okay? So this literally drives the MOSFETs directly. Those then pulse width modulate, send the output to the speaker, which is here, okay? And this is a bridged amplifier, so one side has the audio signal, the other one has an inverted copy of the audio signal, so they drive the speaker output in opposite directions. That's how the bridge works. So while this one is driving one end of the speaker positive, this one is driving the other end of the same speaker negative, okay? That's how a bridge works. That way you get more power basically from the same supply rail. So that's what we have. Continuing this previously ongoing electronics repair thing we have going at the moment, I was looking at the audio input to see whether it was getting as far as these chips. And I actually have like a very small audio signal. I can see it. It's extremely small on the chip. And I did comment that that actually might be normal if these chips have effectively like an op amp on the input. And apparently that's actually what they do have. Let's have another quick look at the datasheet to remind ourselves. And here it is. So this is a typical application. If you look, this is the in. It says in minus, like an inverted input. It shows us in actual fact this is basically like an op amp. We can see it there, okay, on the input. So because the other input is connected to ground, the non-inverting input, and the way an op amp basically works is the feedback network tries to balance the voltages between the two inputs. This acts kind of like, it's called a virtual ground. So the voltage here basically will stay at ground. You won't see a signal, extremely small. I mean, if I put my oscilloscope down to the most sensitive setting, I can just about see a signal on that input. Now this op amp is internally just part of the chip. All this is inside the chip. So you might think, well, where's the feedback that's feeding back to here? And it's external. If you look, this is a drive to the high side MOSFET, high out, low side, low out. VS, this is connected to the junction between the MOSFETs, okay? This is where your speaker attaches from here. So that basically is the output of the amplifier. And if you look from here, through a resistor and another resistor, comes back to in. So that's the feedback. There's a capacitor on here as well to filter out the high frequency switching. This is a Class D amplifier. So basically a proportion of the output, which is going to the speaker, gets fed back to here, okay? And when you apply a signal, the output changes to a sufficient voltage to bring this back down to the same voltage as here. This is the non-inverting input, okay? So this is this virtual ground thing. The upshot is, if you look here, you basically will not see a signal. If you want to see the audio signal, you need to find this resistor and measure the other side of it, okay? So I'm quite happy probably do have a signal getting to these. What I don't have is any output. So with no signal coming in on a Class D amplifier, the voltage going out to the speaker is basically zero. It should be zero. The speaker cone is in the middle position. There should be 0 volts across the speaker. The other end of the speaker is either connected to ground or it's connected to the output of another amplifier in bridge mode. If it's connected to ground, we can say, well, the output here is 0, so that should be 0, okay? For that to happen, these MOSFETs are not switched off. They're actually running with pulse width modulation at 50% duty cycle. The MOSFETs are connected to the plus and minus supply rails, plus B, minus B, in my case 50 volts or something like that. These then are switching on and off alternately at high frequency, 50% duty cycle, so they're both on for an equal amount of time. So the voltage here will be half of the voltage between B plus and B minus, which is 0. Okay, because it is a plus and a minus, so the output is 0. So that's what we should see when the amplifier is idle, and I do not see any drive coming out of this chip, nothing. So we can say that these chips are faulty, and that's not surprising because these MOSFETs were short. Okay, so that is not surprising. Look, they basically connect directly to here through a low value resistor. So this goes short, blows the chip. I have these chips in stock. I had these. I was also somewhat concerned that I have a positive voltage, about 8 volts on one of these connections, which I shouldn't have. So I thought, well, this is coming through these op amps. You see here and here, these channels are the same as each other. This is some sort of protection circuit that controls the relay. So this is what effectively is looking for faults, like a missing supply rail or a DC offset on the output. That's what this does. That's why there's only one of those circuits, okay? But these amplifier circuits are the same. This one has another op amp here. That will be inverting the audio on this amplifier. Remember, Class D, one of the amplifiers has an inverted audio signal, so I'm sure that's what that is for. And we can see that this one actually appears to be damaged. Okay, you can see there, it looks like a scratch, but it won't come off under the microscope. It looks like it's a crack in the IC. So given the fact that I didn't have any of these ICs, TL072, I couldn't complete the repair, but now I do have TL072C. These are op amps with JFET inputs. That's what they actually are. These came from the local electronics shop we have in the capital of Gran Canaria, Las Palmas. So that's where these came from. We have an electronics store here, which is really useful. Costs more than ordering from China, but they tend to be original and we get them quick, so we have those. I've ordered some of these from China as well anyway, just to keep them in stock. So I'm going to replace all three. This one I'm pretty sure is damaged, but I want to see that the DC offset here goes away as well. This is not stereo, by the way. This is not a stereo signal coming from the mixer. This amplifier is mono. It's a subwoofer, so it's single channel. So the reason we have the red, white and black, it's not left, right channel, black as ground. This is what's called a balanced input. Okay. The reason for the balanced input basically is to stop hum on the speaker. We can talk about it sometimes, but I just mentioned that is not a stereo input, okay? It's a single channel audio signal. So that's where we are. The other thing I noted last time when I was looking at this is that we have these which look like transistors, but they're actually TL431 voltage references. There's 2 on each channel. I need to test these as well, and I'll take them out of circuit. Actually, I may be able to test these in circuit. Let's see if we can do that, okay? Otherwise, they come out of circuit. We'll replace all these three. We have 4 of them. We'll replace both of these two. I've already measured most of the resistors on here, especially these which are high wattage resistors. These things tend to fail. These will be part of the feedback circuit, taking the high voltage from the amplifier output back into the feedback for this chip. That's why they are chunky ones. All the diodes, everything else basically tests okay. So let's get this board off. Let's check these. Let's replace the chips and let's see if it works. This is my TL431 tester. I just checked. I made a video about this 3 years ago. Yeah, one of my old videos. I'll link it from the video description to this one if I remember. I'll try my best. And it's a very simple device, you see. So it just has 2 sets of wires attached, the blue and white and a green and white. Okay, you can see it has 1 resistor. The green and the blue are actually attached to each other. That basically is ground, and one of the whites feeds in via the resistor. That's the power in, and the other white measures, you see, and that just goes to one of the end pins. We have 3 pins, and the 2 outer ones are connected together. Okay, can you see that? And the resistor connects to one of those. The middle one connects to ground, the green and the blue. Let me draw it, it's a little bit easier. So the TL431, sometimes called a programmable Zener diode or programmable voltage reference. It isn't a Zener diode, but it has that sort of property. So symbol is like this. And we connect a resistor in series. So that's the actual symbol, sometimes it within a circle, sometimes not. This pin is reference, this pin is cathode, and this pin is the anode. And they come in various packages. The common through-hole one is like this. It looks like a transistor TO92 package. It has 3 pins. So pin 1 is reference. Pin 2 is the anode, and pin 3 is the cathode, okay? Like so. If we take our TL431 and we connect reference directly to the cathode, it acts as a 2.5 volt regulator, or voltage reference, that's what it is. So this is out. This is where we'll find the 2.5 volts with reference to ground. So we have here, this is our blue wire and the white, one of the whites, and then power coming in. We have the green wire and the other one of the white. Okay, so that's how it is. That is our tester. Notice, because reference is on pin 1 and it's connected directly to pin 3, and the anode is pin 2, so that's in the center, it doesn't actually matter which way round I put the TL431. I can put it either way round, yeah, because the 2 outer pins are connected to each other. So I don't have to worry about the polarity. The idea of these is I can go to the PCB, I can find my TL431 and literally just touch it against there. If I read 2.5 volts on the meter, it's good. Now we know how it works, let's do it. The input voltage isn't important. I set it to 9 volts. In fact, this works very nicely with a 9-volt battery. So we'll put the positive on here, negative on here. Put something so they don't short to each other like they just did. Yeah, that'll stop that happening. And then these 2 go to my multimeter, which is here. We'll use this one. It has a nice bright display. Shows up very well on video. So we set this to volts. The blue wire goes to ground, or the black emitter lead. White wire goes to the positive emitter lead. Okay, and we see 9 volts because that's the voltage of the power supply. Okay. Now let's take a TL431 and just hold it against the pins. And that reads 2.5. Okay. Other way around, 2.5. So that's how the tester works. This can actually be used in circuit as well. So let's just go to one of these. That one says 2.5. That one actually gives me a low reading. That one says 2.5. And that gives me a low reading. It could be something in circuit. I can take them out. It's not always conclusive. It looks like I have at least 2 that are reading good. Okay. We'll take them out anyway. Let's double check. Let's give this a try. So we're reading 9 volts. Take one of our TL431s. That reads 2.5. So that's good. They may all be good. Sometimes it doesn't work in circuit. That's good. That one is bad. That low reading. 0.119. And 0.155. Okay, so we do actually have 2 bad ones. It didn't fail us in circuit. They are faulty. We have then 2 bad ones here that we know are faulty. Just mark those 2. In fact, I'll use a white marker. Okay, so those are bad ones. And then we have 2 good ones. Okay, so we'll replace the 2 faulty ones. Those 2 can go back in. I'll change these op amps since I have them, might as well. And we'll change the 2 amplifier chips and we might get somewhere. These are quite easy to desolder, really. There are various methods. I'll show you the one I prefer. If you watch the channel regularly, you will have seen this before anyway. But for the sake of repetition, why not? Yeah. So add some flux, add some leaded solder. Try to get the pins to bridge together. Actually, it's a good move. Okay. A bit on the other side. Yeah, they didn't bridge, but it's okay. It's a little bit tight down there anyway. So what will happen now is the leaded solder will melt before the unleaded solder does, so you don't need to put capped on tape around this. It won't go anywhere. Just aim the hot air away from that capacitor a little bit. Okay, warm it up. Won't take long. That's off. And while it's nice and warm, we can just use a bit of solder braid, clean up that excess solder. I want to get the pads nice and flat, ready for fitting the replacement. So we'll just wick up all the excess solder now. Okay. So that's ready to fit the replacement. And the other ones are the same. With this one, keep the heat away from the plastic. I'll warm the area a bit first, and I won't have to concentrate the heat on the chip for so long. I'll just warm up around here. Okay, let's see what we can do. It's off. Yep, didn't melt anything, Luke. Didn't displace anything. Doing this sort of work as I'm showing you means that none of the lead-free solder ever actually melts, so you can't dislodge other nearby components unless you really get too much heat in. Okay. There are situations where this won't work. For example, when you have a chip that has a hidden pad underneath, usually a ground pad, then this will not really help you. But for these, it's working just fine. This is a little bit more cramped around here now. But we're going to do the same thing. So I've added leaded solder to all the pins. When it's as cramped as this, I don't worry so much about trying to bridge them all. You might end up with a blob of solder falling off, which is not what you want when it's so tight. Okay. Same down here. I have a very nearby capacitor, but we'll do it. Yeah. Just make sure I get some onto all of the pins, that's the main thing. Right. Again, I'll try not to blow the air directly onto that capacitor. It's so close, it's not easy, but we'll see. Once again, you can see that these nearby soldered joints with lead-free solder didn't even melt. So that's how you should try to do this. Don't get so much heat in that they melt, otherwise things may start moving around. You may prefer to put capped on tape around here to stop you dislodging anything else and maybe to protect things like that. Personally, I would say don't do that. You'll make life more difficult because you can't get the heat into the board as easily. But you know, if it works for you, then that's perfectly fine. Whatever works, yeah. I'm just showing you what works for me. And I have done it that other way. I used to do that way, and I found fairly rapidly that it actually didn't help, or at least it didn't help me. Okay, last one. If I'm going to make a pig's ear of one of them, it's going to be the last one. That is always the case. Yeah. Another success. Let's look. That's just a bit of glue or something. Not worried about that. Nice and clean. Those two pads connect together. You can see that. That's nice. This is the one by the connector. The connector is just fine. Okay. Yeah, a bit of glue or something there. Looks fine. Again, that looks fine. I noticed that we don't have two pads connected together on this one, whereas we do on that one. That may well explain why I was getting some different readings around one chip to the other, because the two channels are basically identical apart from the extra chip down here. I didn't actually expect that. I thought they would be wired the same. Just goes to show your assumptions are not always correct. And again, that one's nice. Okay, so putting the replacement chips on is actually probably easier than taking the older ones off. We'll start with one of these larger ones. If we can do this, and the other ones are going to be really easy. So there's a replacement. First of all, we need to put it the right way round. So with the dot towards the end where the notch is. Okay. Couple of ways to do this. One is to put some solder on one of the pads and then slide the chip into the solder. That's the way I usually do this, but I think I might just try it the other way on this one. So we basically get it right. Let's see. Yeah, I think I'll add a bit of solder on one of the pads first. So we'll go with this one. Just pick one of the corners, whichever suits you really. You don't need a fine tip to do this. Look, it's easy enough with a chunky one. So a little bit of solder. Yeah. Now I can clean the tip so there's no more solder left on there. We get the chip. A bit of flux probably be a good idea as well at this point. A bit of flux on there. And now I just need to slide the chip into that little bit of solder. I have the chip left-handed at the moment. I'm right-handed, so I may end up swapping around, but let's have a go. So yeah, I'm going to go right-handed on the chip. I'm not quite so good as my left hand. Okay, you can see I was sliding around a bit there. So we'll go this way. Let's see if I can get onto that corner. I might choose one of these corners instead. Now I'm using the other hand, but let's see. So get our chip. Okay. Coming left-handed with the soldering iron due to not having two right hands basically. Heat it up and slide it in. I've gone a little bit to one side, not a problem, just melt it again and slide it back. You can do it a few times till you get it where you want it, okay? That's close enough. They don't have to be exactly on there. I could possibly move that a little bit more. We can have a go. This is where you'll do it and then wish you'd just left it alone. See what I mean? Right. I'm not messing with that anymore. So there's my chip in position. Still slightly out. My OCD now is coming in and telling me I need to just do that again. But you know, it's fine. Right, let's get the other end. To do this, we want to add flux. I'm doing this using the screen, not my optical microscope. I'm much better with the optical microscope, having stereo vision, by the way. But it's not so easy to show you guys, so I suffer a little bit and do it like this. Okay. Still have a bit of OCD. There, that is better. Okay, so hold it down. Let's just get another pin to go for this one. Okay, we have a couple of pins tagged down now. Hold it down. Just can't quite get in there. Okay, we have a few pins tagged down. Right. Just a little bit of solder. If I get a solder bridge, it's not a problem. I can deal with it. You see, I'm just resting the sharp edge of the tip on each. Oh, there you go. You see that? A little bit more. I'll do the other one under the optical microscope. You can see the difference it makes for me, okay? Just out of interest, so I'm running a bit low of solder now. Maybe I just need to load it a bit from one of the pins with more on. Okay. Again, I can just load the tip from that one. Touch more. Okay, let's have a look at that. I'll just clean it up. Okay, looks fine. So I actually did that using the overhead camera on the bench, not the microscope. I can bring the microscope in now. We can have a closer look. So this is the USB microscope. There you go. So you see I have not far different on the magnification using my overhead camera, by the way. I'll just show you in a moment, and then we'll go to the optical microscope. This looks all right to me. All the pins look soldered. There's the odd one that hasn't got so much solder on, but it's certainly soldered down. Okay. There, let me know out of 10 what you think of that one. I'd give it an 8, probably. That's the overhead camera. I have shown it before. This is a Sony HD, what is it, AX2000, I think, Handycam, yeah, something like that. I've made a video on all the equipment. I'll link it if you want to see it. Okay, so that's the actual camera I'm using, which you can see gives me very good magnification actually. This is the optical microscope, so I'm going to do the other one using this. The big advantage here is I have stereoscopic vision, so let's see if I can actually do the job better. So with the optical microscope, you can't really demonstrate this to people unless they look through the microscope, because what you are seeing is the camera that's mounted on the microscope. So for you, you still have the same sort of vision as you would from the USB. In fact, I'd say the USB microscope is a little bit clearer than this one for the camera. But what I see down through the lens is wonderful stereoscopic 3D vision, okay? I also have a wider field of view through the optics than you have on the camera as well. So that means sometimes when I'm doing it this way, I tend to drift off. So there's our chip. But I'm going to do the same thing as before. I'm going to position with my right hand, solder with my left hand. So I'm going to add some solder onto one of the pins, or rather one of the pads, and slide the chip in. And let's see if I can do it better. So, bit of flux. I'll use the microscope, that's the whole point. Okay. A bit of solder. Okay. Get the chip in my right hand. It's the correct way round, okay. Just put it to the side of that little soldered pad. Okay. So I can position this much more precisely. Yeah. First time. I can move it slightly, by the way, when one pad is tagged down, just very slightly, so that I can actually now come in with a little bit more solder on this pin. And I can just melt that again and just straighten this up a little bit, so I now have the tweezers in my left hand. It's okay. Yeah. Okay. Add flux. And just tag it down, pin by pin. See? Another thing with this microscope is the camera sometimes focuses slightly different than the actual optical image as well. So when I have it perfectly sharp, you may have it just slightly blurred. Can't really do anything much about that. Get in that one. This capacitor's in the way a little bit, but it's okay. There. Let's clean that one up. Okay, so that's the one I soldered using the optical microscope. You'll notice these chips are the opposite way round, by the way. I haven't put one of them back to front. You can see the little groove thing there, okay, on that one. And this one, it isn't there. Look, it's actually at the other end, but this one isn't quite centrally positioned, so you can't see it easily. You can see it before I soldered the chip, so you know it is the other way around. And that's the other one. So I have to say, this is kind of like a 7 or 8 out of 10, I think. And that is more like a 10 out of 10. So to me, and I hope that kind of demonstrates this, a lot of this, as well as just practice, really, experience, also comes down to the equipment you're using. Yeah. I'd like you to comment on that below, what you think, but to me that is the easier way. And if I wasn't making videos to show you guys, I would be using the optical microscope. Always. And here are the replaced op amps, TL072, one of them, and 2 on this side. Okay, you can see it. I did these with the optical microscope. They're all pretty good, I think you would agree. Right, so we need to put this back together and try it. Well, it's time to try this, guys. It's all put back together. All those chips are changed. Those TL431s are changed. I have the current limiter set on at the moment, although in fairness that did not save it the first time when I fitted those fake MOSFETs, yeah. But we can only try, so switch on here, you can watch the lights, you can watch that light, and what does it do? It powers up, yeah, you saw the light go a little bit brighter again, it came to on, so it powers up. So we just have to connect an audio input, connect our woofer again. This is a subwoofer amp, and let's see if it works. I mean, there's no protect light on, so that at least is a good sign, but there again, there wasn't before. I just didn't get any audio. I have my mixer attached. The mixer's turned all the way down at the moment. I have a sub speaker attached. Let's see. Power on. Power on. Do we get any sound? No. We get a signal, but no sound. I'm going to attach my own speaker. I'm just not 100% sure this sub is actually working. It's a passive sub. It's one I repaired with a split cone that I can't really give back because it's not good enough, but should be good enough for testing things with. That is the theory. Okay, so I'll connect my speaker. These are just full range speakers. But if I keep the volume down, we should be safe enough. So again, power up with my speaker attached. Yeah, signal. And we still have nothing. So this amplifier still defeats me. Yeah, after all that, it still defeats me. I'm determined to fix this, but it's just getting like further and further in depth. But hey, you have to do it sometimes, yeah? Okay, I did think that would work today. It doesn't. I think we need to get the scope out and go around, but this video is too long, so I think it's Friday. I'll carry on with this one on Monday. Okay, see you all soon, guys. I won't say ciao for now. I'll just say I'll be back.